In the last class, we discussed numerical integration and the basic rules for numerical integration, or the basic theoretical foundation for numerical integration. So, we just summarize before we go into the next step of polynomial approximation to the integration. We will just go through, we will summarize what we did in the last class. So, the idea was to use replace an analytical formula of this type for an integral of a function between the intervals between the interval a to b by some numerical method that will be necessary in cases where this function itself is the functional form is not known, or sometimes even when the functional form is not known, but the integration is difficult or impossible analytically. So, we said the basic idea here would be to approximate the function by a polynomial of order k, and then say that the error in the polynomial would be then of this form, that is here psi k being the product of x minus xj between the intervals for all values starting from 0 to k. This is order k plus 1 term here. So, that is order k polynomial plus an order k plus 1 term, and we know what this coefficient is from the divided difference. So, then we said that okay, now if you approximate it that way, then we have the error in the polynomial as the difference between the integrals of these two, that is integral of the function, which is the actual function which we do know, and minus the integral of the polynomial, and that will be this particular term. And then we looked at two different cases, that is so in this error two different cases was especially analyzed. One case where this term psi k of x is of the same sign in the whole interval a to b. In that case, we said that using the mean value theorem, I can write the error. So, if this is of the same sign whole through the interval a to b, then I can approximate this error by f evaluated at some value zeta between the interval a to b multiplied by integral psi k of x dx. This is, and then using the mean value theorem, we can say that this is given by the k plus 1 derivative of the function divided by k plus 1 factorial at some point eta. Okay, now, this is true only if this is of the same sign, that is psi k of x, that is this order k plus 1 polynomial is of the same sign in the whole interval between a to b, that is in the interval a to b. So, that case we can use this, okay, and then we saw that in another case where even when that is not of the same sign, but a special case again that psi k of x dx in the interval a to b is 0. In such cases, we can again write that coefficient, that term then in the error, the first term in the error, that is the f, this term we can replace by a k plus 1 order term. This by using the divided difference method, okay, which you have learned in the polynomial interpolation. I can use the divided difference method and write that kth order term into a k plus 1th order term as a k into something which is of a k plus 1 order term. So, that is then from that you can say that now the new function, that is the psi k into x minus x k plus 1, that is now this thing will be replaced by psi k into x minus x k plus 1, and then if that is of the same sign, then I can write this error as f of f, this k plus 2 derivative of the function f. So, that was a basic foundation. And then we said that now if it is not true, that is if this term, that is x minus x k plus 1 into psi of k is still 0 in the integral of this. Assume that x minus x k plus 1 into psi k of x is still 0, the integral of this is still 0, and then we can go to a k plus 2 order term, and then write it as the error as now error will now become something of the order the derivative of, so the k plus 3rd derivative of the function. So, in that way we could go to very large order and accuracy. So, that is what we said, and then we looked at three different cases. Actually, we looked at two different cases yesterday. That is, one case was what we call the rectangular polynomial, rectangular method for approximating the integral, and that is replacing the function f of x by p0 of x. So, the idea was that all this the integral a function f of x of this form, if you have a function of this form and then if you want to integrate that function between the limits a to b, what we mean by that is actually finding the area under this curve. So, that is what we mean by actually finding the integral of this curve, right. So, now in the first approximation, the rectangular case where we approximate the function f of x by p0 of x, we are actually finding the integral will turn out to be I of p0 of x, that turns out to be f of a into b minus a in the rectangular approximation. That is, we have a polynomial of order 0 and the tabulated value is at in the beginning, in the beginning of the interval, then it is f of a into b minus a, that is the area under this particular box here. Okay, so that will be the area under this box. That is one method which we looked at. Okay. Another method which we looked at was to say that we will not, in this case the error is of the order first derivative, okay, the first derivative of the function. So, that is the error in this order for first derivative. Okay. And the second case we looked at is to say that we can tabulate the function at the midpoint between the interval a to b. In that case, we have a case where x minus x0 dx, that is psi 0 of x minus x0 dx is 0 instead of being 1 sign. In the earlier case, it was 1 sign, that is when we took tabulated the function at the first point of the interval, the beginning of the interval, but now we tabulate the function at the midpoint of the interval, and then psi 0 of x integral a to b dx is 0. In that particular case, we can write the integral as b minus a f into a plus b by 2. Okay, so, that is saying that now I will not do this, but instead I have the function f of a. Now, f of x versus x. So, it is a function like this, and I am tabulating. This is the interval which I want to do, right. So, that is a and that is b, but I will tabulate the function in the middle here, f of a plus b by 2. Okay, that is a plus b by 2, and I have the function value at a plus b by 2 here. And then I will compute the f of a plus the I p0 of x in this case is f of a plus b by 2 into b minus a. So, that is the integral, and so here it is f of a into b minus a, it is f of a plus b by 2 in b minus a. So, it is a different box, and the box would be like this. Okay, so, now the box which we are computing the integral as the area of this box is what we are now computing. Okay, so, you can see that both of them have error. So, this has the error by this amount, and while this has an error by this amount and this amount. And you can see that the error here, the error is here of the second derivative. Okay, error here is the midpoint in the integration. Okay, the error is in the second order. Okay, that means if the function is the second derivative of the function is 0, then the error is 0. That you can see straight away. That is, the function was a straight line here, okay, with second derivative 0, and then this positive error will cancel with this negative error here. Okay. So, then you will have an exact integral here. Okay. So, in both these cases we have error, and we are just using simple idea that we just construct a box and then find the integral of area under that enclosed by that particular box. And I should say that all these methods, these two methods especially, can be used as you do not have to cover the whole interval by this. You could split the interval into separate intervals and then evaluate this integral in succession. That is, I could take this particular case and then say I will split this into many boxes instead of one of them. Okay, so I can split this interval a to b now, okay, which I have. Okay, now this interval a to b I have. Now I can, so I had this interval a to b, and I can split that into smaller intervals, right, a1, a2, etc., and then compute the area under each of them using the using the rectangular rule or a midpoint rule. Okay. I could use either the rectangular rule or a midpoint rule to compute the area of the error, the area under each of this rectangle. So if I use the rectangular rule here, I will go in and do this. I do this particular area for first, and then I will do this particular area. Okay. I will still have an error because of this little boxes here, little triangles here will be left out. Okay, but it will be much less than the earlier case. So you can improve the accuracy of this integration by going into smaller rectangles, and same case here too. Okay, you could go into smaller boxes and then improve the accuracy. That is to say that you can improve the accuracy by either reducing the interval b minus a, that is go into smaller boxes, split the whole b minus a interval into many intervals, and then you can increase the accuracy. Okay. So now these are the two methods we have looked at. So the midpoint rule and the rectangular rule, and that's both was order 0 polynomial. Okay. Now we look at the case where we approximate the function by an order 1 polynomial. So we now look at polynomials of order 1, that is approximating the function f of x by a polynomial of order 1. As we write f of x as f of x0 from the Newton's form as f of x0 plus x0 x1 x minus x0. So that's our polynomial of order 1, and then we will have an error term which would be of this time. So that's the error term. So this is psi 1 is x minus x0 and x minus x1. So x0 x1 x. This is our error term. So now again we have to make choices for x0 and x1, and we look at this particular case where 0 and x1 are chosen at two different ends. Okay, so now that's the case which you are going to look at. So now we are taking the function f of x, and then we are choosing the two intervals. We'll choose a similar type of function, and this is my x-axis, and this is, so we'll have a function like this, and then we choose the interval a and b, and we are going to take the function value, evaluate the function values at these two, tabulate the function values at these 2 points, f of x, f of a, and f of b. That's what we are going to use. So in the whole interval a to b. So that means the psi 1 of x is now x minus x0 into x minus x1 will become x minus a into x minus b. x0 is a and x1 is b. That's the polynomial which we have, and then we can write the integral I of x. So we wrote the polynomial here. So the function we have to now approximated by f of a, right, plus f of b minus f of a divided by b minus a into x minus a. So that's our function, and then we have this error term here, which is which I said f of a b x into the square bracket is a coefficient, and x minus a into x minus b. So that's a polynomial. So the integral I of f, well now this is approximation to the polynomial. So I should write this actually, f of x approximated by p1 of x equal to that. Okay, now this I of f approximated by I of p1 of x in the interval a to b, right. So that is so that would be the integral of this, right. So that is f of a into b minus a plus x squared minus a evaluated in the interval b to a, x squared minus a by 2 in the evaluated in the integral a to b. So that is f of a into b minus a plus f of b minus f of a divided by b minus a into x minus a whole squared by 2 into interval b to a. And that's approximation, and that's an error term next to that. So you can simplify that and write this in this form. So the integral will be now become b minus a into f of a plus f of b by 2. Okay. So now graphically this is the same as drawing a straight line from here to that, okay, okay, and taking the area under this curve. So that's what we are getting here. So this integral, which is actually f of a plus f of which is equal to b minus a by 2 into f of a plus f of b. Okay, so that's same as finding the area under this curve, which is under this trapezoid, which we get. Okay, so hence the name called the trapezoidal rule. Okay, in which we will actually draw a line from here to there. Okay, the two endpoints, and then find the area under that trapezoid. Okay, so you can see that it's actually this term which we are getting here. Okay. So what we are getting these two together is actually the area under this rectangle here, and then the area under this triangle. So that's what we are getting these two terms here. So that's a sum, okay, which is actually the area under the trapezoid. So hence that name trapezoidal rule. So now the error again here in this trapezoidal rule, which is represented by ET. Okay, so we had ER for rectangle, EM for midpoint, and ET we use this. Okay, that is again of the order second derivative in f, okay, into b minus a q by 12. Okay, now the reason being that again, as I said, so the error term, that is x minus a and x minus b. Now this is of one sign in the whole interval. Okay, so hence so x is always less than b. Okay, so that is negative, and x is always greater than a. Okay, this term is positive, so the whole product is always negative. It's of one sign, and hence we can write this as in this form, in the error as in this form, and that error is of the order of the second derivative for the interval a to b. Okay, so this is another case where we get an order second derivative of the function, the error of the order second derivative of the function. So again, notice that we don't have to use this method for the whole interval at one shot. You could again split this into smaller intervals and use them and find the area of each of the trapezoid in between. The accuracy in that case would be pretty high, as you can see here. So that is the case of the first order polynomial called the trapezoidal rule. So now, so far we have looked at three, that is rectangular, midpoint, and the trapezoidal rule. So you could do this problem, that is, you could just take cos squared x dx between the limit 0 and pi by 2, and we know what the integral of this is analytically, and then you could evaluate them using rectangular, midpoint, and trapezoidal rule, and you could calculate the error because you know the exact value of this function, and then you could compare them with what you get. Okay, so now so far we have looked at order 0th order polynomial. Okay, that is in the case of rectangular and the midpoint rule, and then we looked at the first order polynomial, and that's the case of the trapezoidal rule. Okay, so now we will look at order 2 polynomial. Okay, and that's the case in Simpsons rule. Okay. So we will look at order 2 polynomial or approximation of the function by an order 2 polynomial and its integral. Okay. So again, we will write now the function. The method is now you can see that the same method. It's just that we go to a higher order polynomial, and we have to tabulate the function at now more number of values, a new number of points. Okay, so we say f of x is p2 of x plus f of x0, x1, x2, psi 2 of x. So now this will be now an order 3 polynomial here, this error term, and an order 2 polynomial here. So we need to now tabulate the function at 3 different values. Okay, and in the Simpsons rule, we choose that points to be a plus b by 2. So you can see that the integral of this would be, the psi of x would be 0. So that's what we are going to use here, x0 equal to a, x2 equal to a plus b by 2, and x1 equal to b. So in this case, we are going to use 3 different polynomials. We are now substituting it by a polynomial of 2. So our idea now will be f of x is now p2 of x plus some error term, right? So now the p2 of x is now given by f of x0 plus f x0 x1 x minus x0 and plus f x0 x1 x2 x minus x0 into x minus x1. So that is this is approximation to the function. So that is f of a. We are choosing x0 to be a. So x0 is a and x1 is a plus b by 2, and sorry, it's x2 to be a plus b1 by 2. This is important. X1 is b. Okay, that's what we are going to use. So then we can substitute that and write p2 of x now as f of a, right? And x1 is x0, x1, and x1 is b. So this term would be now b f of b minus f of a divided by b minus a into x minus a. Right. So now this term will now be, this term will have three terms, that is f of a plus b by 2 minus f of b minus of that with f of b minus f of a, now divided by, so sorry, this is b minus a plus b by 2, that is here, and this would be b minus a. Now divide the whole thing by b minus a, b plus a by 2. So the whole thing would be divided by a plus b by 2 minus a. Okay, that's what we are going to get the as the into x minus a into x minus b. Okay, that's our polynomial. Okay, so now that's a polynomial we have. Okay, the approximation, and we can now find the integral of that. This is just a polynomial, so we have to find the integral of x minus a and x minus a into x minus b between the interval a to b. Right. That gives us. Okay, so I have summarized, shortened this here. So if we do the integral, okay, we will get this as b minus a whole square by 2, and then b minus a whole cube by 6. Okay, so this is the last term. Okay. So we have the coming as x minus a whole square by 2 and x minus a and x minus b integral, where that will give us b minus a whole cube by 6. So that's the thing. So we just integrate this function, and that's our approximation under the Simpsons rule. Okay. So here we are now approximated the polynomial by a second order polynomial. So it's not a straight line anymore. It's a curved. It's a curved line with. So it's a curve. So again, this second order polynomial. So we'll be now actually using some kind of a curve to connect these 2 points, right? And then calculating the area under that curve. So obviously that would be much more accurate than this in cases where the second derivative of the function is non-zero. Okay. So in this particular case, Simpson's case, now we have taken 3 point samples, right? So we have taken A, B, and we have taken one more sample here. Okay. So that is f of a plus b by 2. Okay, so we have taken one more sample there. Okay, so now our curve now, and we approximated this curve by another some polynomial of this form. Okay, so that will be the thing, and then we find the area under this whole curve. So that's what Simpson's rule do. Okay, and in the cases where the function is not so smooth, okay, where you have for example, the function could be need not be smooth in the interval a to b. So you could have f of x versus x has some curve like that, okay, not so kinky but smooth. Okay, in that case we could again split this into different intervals, okay, smaller intervals, and then evaluate the integral for each of this interval, okay, and then compute this total integral as a sum of all those integrals. So that's the Simpson's rule, and here the error would be obviously the order 3. Okay, in the case where So now this is the final answer which you get it as, okay, the formula. So f of a, finally the answer would be get is the P2 of x would be b minus a by 6 into f of a plus 4f into a plus b by 2 f of b. Basically just the integral of all of this. Okay. So if I do integral of this and sum to the integral of this between the integral a to b, between the limits a to b, then I would obtain some formula of this form, a formula of this form. So again I can write down the integral of the function in the interval b to a to b as a sum of 3 terms, okay, each containing the function evaluated at that particular point, that is a plus b by 2 and b. So f of a plus f of b plus 4 times f of a plus b by 2 into b minus a by 6. So that is the Simpsons rule. Okay, so if you are implementing this, is again a very simple formula to implement. Only thing is you need the function value at 3 different points to evaluate this. And where the case the function varies much more rapidly than this, we will have to split our interval into different smaller intervals and then use the formula, this formula in each of that intervals. We will yet use this formula in each of those intervals. That's the idea. In all of these methods that we would have more rapidly varying function, then you would split them into smaller intervals and then evaluate it. Of course, more computationally intensive and also more probability for a round of errors. So that is why we look at better methods with higher accuracy, which we can go for larger intervals, because we split them into smaller intervals and then we have to do the many calculations for each of this interval, then we will have more probability for getting round of errors dominating the value. Okay, so now we look at the error in the Simpsons rule. So error in the Simpsons rule is now of the order 4. Okay, now the reason being this, that the error term, that is x minus a into x minus b into x minus b. So in the Simpsons rule we had the psi 2, right, psi 2 of x, and that is x minus a into x minus b into x minus a plus b by 2. Okay, so now this term vanishes, this integral of this vanishes in the limit a to b. So we have a higher order accuracy here. So what we get here is actually a 4th order term. Okay, we can go one more order up in the error. So 4th order derivative is the error is of the order of the 4th order derivatives of the function. Okay, so that's this may be by the most accurate method which we've seen among the 4 methods we have looked at so far. Okay. So we'll just compare now all the 3 methods which we have looked at. Okay. So for integral of a function f of x, the numerical integration of a function f of x in the interval a to b. Okay, so we have the rectangular rule, okay, which said that it is the integral is b minus a into f of a. That's what the rule said, the rectangular formula. So we evaluate the function only at one point and multiply it by the interval. That's the rectangular formula. Okay, graphically it is just this. So we have a function like this, right, and then we just evaluate the function at one point, okay, and calculate the area under that rectangle. Okay, that's graphically the rectangular rule is. Okay. And then we have the midpoint formula, which is b minus a into f of a plus b by 2. Okay. So again function is evaluated only at one point and then we multiply it by the interval b minus a. So this calculating the area under again a box, but now the function is evaluated at b plus a by 2. Okay, that is in this box. Okay, that's the area under this shown as in this red color region here. And that's the second formula which we looked at, the midpoint rule. And then we looked at the trapezoidal rule, which had the formula as b minus a into f of a plus f of p by 2. Okay. And that's again the area under this particular box, that is a trapezoid. That is a straight line connecting a to b, and then the area under that particular line is. So the area under this curve is now approximated by any area under the line connecting f of a to b. Okay, so in this case, again this will be exact if there is the second derivative of this function is 0. that is if it is a straight line, obviously. Okay. And then we looked at the Simpsons rule, and so the trapezoidal rule was order 1 polynomial, and the Simpsons rule now we use an order 2 polynomial, that is, a function has to be now evaluated at 3 different points, and we choose them to be a, b, and a plus b1 b by 2, and then we obtain a formula as b minus a by 6 into f of a plus 4 f of a plus b by 2 and plus b f of b. So now that's the Simpsons rule, and now that amounts to actually fitting a curve between these points, okay, a curved region, and then finding the area under that curve. So that's the Simpsons rule. Okay, so now to summarize all of them together, it will be a comparison of all the methods will be this for a function of this form. Okay. So the approximation to the area would now be given by these four different boxes. Okay, so you could have the area under a rectangle, okay, area under a trapezoid, okay, area under another rectangle, but now centered at f of a plus b by 2, and the area obtained by fitting a curve of second order polynomial through these 2 points. Okay, so that's a summary of the rules which we have seen. Now of this polynomial approximation, of this simple polynomial approximation. Now we go to a slightly different method at evaluating integrals numerically, but again in a sense using the same basic idea that we can approximate the function by a polynomial, and these rules are called Gaussian rules. Okay, so they are obviously they are used because they are a little more complicated in concept wise, okay, but the accuracy is much larger than these simple polynomial, these approximations which we saw as a rectangular, midpoint, or trapezoidal, or Simpsons rule. So now these new things of rule, new method are classified as Gaussian rules, and we look at them now. Okay, so that is a little more complicated than what we saw now, but much more accurate than the simple rules which we saw. So in the Gaussian rules, the idea is to, again, as I said, to write the integral of the function as the integral of a polynomial of order k. And we want to write in this method, we want to write this as a sum of the function values evaluated at these different k points, okay, that is x0 to xk, k plus 1 points here, and multiplied by some coefficient a0, a1, up to ak. So the idea is to write it as a sum of some weight multiplied by the function value. Okay, so that's what I said. It's basically the idea of the polynomial of the approximation is the same, but now we want to write the formula, okay, in this form. Okay, that is the function value evaluated at that point and then multiplied by a weight, and the whole method is to find what these weights are. So we tabulate the function values at some x0, x1, and then we have the function values at that point x0, x1, and then we compute the weights of at this a0, a1s, and then we just find the sum of this product. Okay, so that's a weighted sum of the function value. Okay, now we have to choose. Now the clever idea here is to choose these points x0, x1, xk, etc. They are not arbitrarily chosen, and we have to choose them such that the error, if you choose k points, okay, the error, or if you choose n points, the error will be of the order of 2n plus 1th derivative of f of x. Now note that in the case of rectangular or midpoint rules, we have chosen a function of a polynomial of order 0, or polynomial of order 0, and then we had accuracy of order first derivative of the function or second derivative of the function. And in the case of Simpsons rule, for example, we had chosen a polynomial of order 2, and then we had an accuracy up to 4th order derivative of the function. But here we are talking about evaluating the function at n points and getting an accuracy which is the order 2n plus 1th derivative of the function. Okay. So, you can see why these methods are the best to use for numerical integration, where we have the freedom to choose the point at which the function had to be evaluated. So, it may not be possible all the cases, but in cases where it is possible, that is where we can evaluate the function at the points of our choice, okay, and then these are the best methods to use. So, we will now look at what the basic idea of this method is. So, the method is the following, that we write the integral f of x dx, that is I of f, now is approximated by I of g. Okay. So, where g is another function, so I will write g f of f as g into w. Okay. So, let me write that here again. So, we want to find the integral of f. So, I of f. Okay. So, which is actually integral some a to b f of x dx. Okay. So, now I want to approximate this function by integral a to b, yeah, g of x, some other function g, into w of x dx. Okay, so I want to write this as a product of two such functions, okay, and evaluate and I want to now write the integral of this g. Okay, that's what I call I of g. So this is equal to, now I would use this as I of g to denote that I have actually split this function f into two values, g and w. Okay, now this is particularly of interest where this f of the function f of x itself may not be very well behaved, but the integral is finite. Okay, for example, if you have a root x sitting in the denominator, okay, and you want to integrate it through a limit 0 to something, 0 to 1 or something, or minus 1 to plus 1, okay, then you will have trouble evaluating this function at 0. If it is 1 over root x, but the integral itself is finite. So, in that particular case, this is actually useful to write this as a function, a well behaved function in the interval a to b multiplied by a weight, some kind of weight w of x dx. So, as I said that there will be cases where f of x is not well behaved, but the integral is finite. Okay. So, in that particular cases, where in that kind of cases this is particularly useful. So, then what we do is now we do not approximate the whole function by the polynomial, we will just approximate the function g by the polynomial. Okay, that is the idea. So, earlier we were approximating f as a polynomial, okay, but now we will not do that, we will approximate the function g by a polynomial. Okay, so, this is the Gaussian rule, this is the first step. Okay, so, we have split the function f into another function g and a w, okay, and we now use a polynomial approximation, but not for the whole function f, but only for g. Okay, so, that is as I said is particularly useful when the function f of x is not well behaved in the interval, but the integral is a finite integral. So, then we can use that and write the polynomial now in this fashion as before. Okay. So, that is the first step. Now, we are familiar with this, that we now write instead of f of x, we write g of x as pk of x, that is some polynomial of order k and an error term into psi k of x, where psi k of x is now order k plus 1 polynomial. Okay. So, now given that we can write the error I.e. as I of g minus I of p of k, the error in the integration as I of g, as I said, is I of f, but now the error is slightly different from what we had written before, because now g was f into w. So, the error is actually g x0 x1 xk x into w of x psi k of x dx. Okay, so, now we have this extra function sitting here, psi k f x is the same as what we have used before. So, then if we have now, as we have done before, now we can again argue that if this whole quantity, the integral of this quantity, that is integral w of x psi k of x dx is 0, then I can, as before, write g x0 x1 xk x as two terms, that is g x0 x1 xk plus g x0 xk x1 xk plus 1 x into xk minus xk plus 1 minus xk. That is, if integral integral psi k of x into w of x dx is 0 between the limits a and b. Okay, if this is true, then we can use the fact that g of x0 xk x can be written as g x0 xk, then plus g times g of x0 xk plus 1 x into xk plus 1 minus x. We have seen this earlier from the divided difference method, right. So, I can replace this quantity by this quantity, and we know the integral of this is 0 when this is 0, right, because now my error term is now going, which is g x0 xk x into psi k of x w of x dx will now going to have two terms. One is integral g x0 xk w psi k of x w of x, right. That is the first term dx, that is coming from this, and then we have another term which comes from integral g x0 xk plus 1 x xk plus 1 minus x psi k of x w of x dx. Okay, so we had these two terms. Okay, so we have a term which is so this integral, now this integral is now split into two terms. Okay, one contains one from using this divided difference thing, and we know that this is 0 because this is a constant and this integral is 0, and then we have this term which becomes psi k plus 1 of x. So, we know that the order of the accuracy has gone to the k plus 2th derivative of the function f. That is what has been summarized here. Okay. So, we use this idea that if this is 0, we can go 1 up in the accuracy or in the derivative. Right? The error becomes of the order of the next derivative, that is k plus 2th derivative, okay, if this is 0. So, now the idea is to choose the functions, the values x0, x1, x2, etc., such that the order can be pushed up to 2k plus 1. Okay. So, that is what we have mentioned this earlier. So, now I want to choose, so now I choose a new point k plus 1, right. So, now I choose the k plus 1 such that w of x, sorry, there is a mistake, w of x x minus xk plus 1 x up to all this thing is 0. Okay. So, w of x. So, now the idea is, as I said, so now we choose this function such that, so we had this w of x psi k of x dx equal to 0. So, that led to, this led to our choosing a new point k plus 1, okay, and then evaluating the error as w of x psi k plus 1 of x dx. Okay. Now, let us say we chose the k plus 1 point, okay, and so this had this g which goes from x0 to xk plus 1 x w of x psi k k plus 1 of x dx. Now, we chose the new point k plus 1. Okay, now, we choose it such that this integral is again 0, that is integral w of x psi k of x dx is 0, and then this will lead to integral g of x, so integral g x 0 x k plus 2 now x w of x psi k plus 2 of x dx. Okay, so we can continue with that, okay, and then go up to k 2k plus 1 n order which we want to do. Okay, that's the idea, right. So we have to now choose this points k plus 1, k plus 2, k plus 3 up to k plus m, let's say, okay, such that this integral, that is w of x, that is integral w of x. Okay, so we want to continue with this. Okay, so we continue with that, and then write, we choose point up to such that w of x psi k plus m of x dx is equal to 0. So we will choose points up to that. Okay, so k plus m would mean that, you know, w of x into x minus x k plus 1, x w of x into x minus x k plus 1, x minus x k plus 2, x minus x k plus m dx equal to 0, right. So we want to write all the way up to that. Okay, all terms are 0. Okay, then you have an error which is of this form. Okay, and then we have the accuracy would now be g, that's the k plus m plus 2 derivative of the function g. Now, if m is k, that is 2k plus 2 derivative of g. That's the idea. So now the question is, how do we choose this point? So the idea of Gaussian integration or Gaussian methods is to choose the point. So it is to provide a method of choosing these points, that is these points x k plus 1, k plus 2, k plus 3, k plus 1, okay, such that we have the error, an accuracy of that order. Okay, so that is what we call the Gaussian method. Otherwise, it's not very different from what we have done earlier. So there are two differences. One is we split the function f into g and w, that is g into w, and we choose the points such that we have, and this method provides, or this in the Gaussian methods provides a way of choosing these points k plus 1 to k plus m such that our accuracy is of the order the 2k plus 1th derivative of the function. Now, what is the polynomial? To do that, we write the polynomial in the Legendre form. Okay, we have seen this in the polynomial interpolation. Okay, so we write the polynomial in the Legendre form. Okay, that's now when you want to write g of x as p k of x, right. So the two steps. Let's write the two steps. That is the function f of x which you want to integrate. Right, we write that as g of x into w of x. Okay, and then we approximate g of x by p k of x. Okay, so now that we write in the Legendre form, that is integral I going from 0, sorry, some I going from 0 to k, and then pi, okay, into x minus xj divided by xj minus xi for j not equal to I. So for j going from 0 to k, but j not equal to I. Okay, so that's what we had written. Okay, sorry, g x of I minus xj into g of xi. Forgot that. Okay, so that's the idea for form. Okay, we will write. So we have written this in the polynomial interpolation case. So you have a sum of the products. So the products are x minus xj by xi minus xj and g of xi. So that's the. So we have to evaluate this product and then multiply it by the function and then take the sum. Okay, that's the polynomial that is a Legendre form for the polynomial approximation. So now we know we can choose this Legendre polynomial approximation. So we can choose the points x values to which the function has to be evaluated as the zeros of this polynomial. Okay, that is the basic idea of Gaussian integration. We will see that now. So first we write the polynomial approximation to g of x in this form. That is I going from 0 to k, j going from 0 to k, where j is not equal to I, x minus xj divided by xi minus xj into g of xi. So that is a polynomial approximation to g, the function g of x. Okay, and then the integral can now be written as this, right. So I of pk is obviously the integral of that particular function which we just wrote down, okay, multiplied by w, okay, in the limit a to b dx. Okay, that is the function, that is the integral. Okay, so we want to evaluate this integral in this limit. Okay, so now this function is evaluated at xi, so that comes out of the integral. Okay, so I can interchange that. I can take out this integral. Okay, so what I have to do is evaluate this integral, this integral of this product. Okay, so that's what you have to do. Okay, and then I will write that as a function. Okay, so I'm going to write the integral I of f, okay, as integral of this sigma I going from 0 to k, pi j going from 0 to pi is a product going from 0 to k, j not equal to I, x minus xj divided by x minus xi minus xj into g of xj xi into w of x dx. So I can take out this, I can write that as sigma I going from 0 to k, okay, integral a to b, now a to b, right, pi j 0 to k, j not equal to I, of x minus xj divided by xi minus xj w of x dx. Okay. Now I will have here, sorry, one term I missed, that is sigma I going from 0 to k g of xi. Okay, so this is the integral, and then there is a function. So I can write this finally as sigma I going from 0 to k g of xi into some w I, g of xi, so w of xi. Okay, now this w being different from that. Okay, so this is okay. So this w is different from that. This is just this is a weight. So this is the integral. This whole integral I am representing as the sum w of xi. So I can write it as a sum of the function value evaluated at these points, xi points, multiplied by some integral. So each of these xi's I will get one value from this integral, and I substitute that here. Okay, so that's okay. So I use the word a there. So to distinguish, I will write it as a of xi. Okay, some weight. Okay, to distinguish it from w, I use it as a of xi. Okay, so that's what's shown here. Okay, so now thus the integral is now reduced to a weighted sum of the function values at a set of points, and the weights are given by this integral. Okay, so x minus xj divided by xi minus xj into w of x dx. Okay, so that's a weight. Okay, so now we will just look at the error term. Okay, with the last, so the error term will now be of the order of k plus 2. Okay, we have chosen that the error in the integration will be k plus 2. Okay, and then but we have chosen the k points. Okay, now we have to choose the k points such that the function value, this integral is 0. Okay, so that is done by choosing this. Okay, so we will choose the k plus points such that they are 0 to I itself. That is, we will choose k plus, okay, we will see, the idea is that we will choose this k plus xk plus 1, xk plus 2, x2 up to x2k plus 1 as x0, x1 and xk. Okay. So, if you do that, then we can get the order of 2k plus 1 accuracy. Okay. So, first let us assume how do we arrive at that? Okay, we just to see that. Okay, let us assume that we get this 2k plus 1 points to be of this form such that this integral is 0. Let us assume that we can, there is some way of choosing this k plus 1 points, that is xk plus 1 xk points. So, that is xk plus 1 to x2k plus 1 such that this integral is 0. Okay. And then since this psi k of x is this product, okay, then that means this is of the order of 2k plus 1. This polynomial, this whole polynomial is the order 2k plus 1 because this is already of the order k plus 1. Okay. And so, we will write this as two different polynomials. Okay. We will write this as psi k, which is of the order k plus 1. We will write that as some alpha k plus 1 into psi k. Okay. And then we write this whole product here as another polynomial. Okay. And then we will demand that this this sum should be 0. That is, we have two polynomials. One is k plus 1 order, and then is m, which is also of order k, and we demand that this integral should be 0, and then choose the points x0, x1, xk, and we see that this product is 0 if we choose x0 to be xk plus 1 to be x0, xk plus 2 to be x1, etc. Okay, and then we have an accuracy of the order 2k plus 1. We will see more of this in the next class. We will go through this last part once again and look at how we arrived at this particular form for this and the implications of that in the actual calculation of the integral. We will do that in the next.